All right, any other questions on the homework before we move on to continuity? Does anybody is anybody done with this assignment and kind of want the next one?
You can give the next one.
Yeah.
You can give the next one.
Okay, I'll have to make it up, so I'll like put it up on World Class.
Oh, you don't have, okay.
I'll do it like after class in my office.
You know, never worry about giving us too much work.
Never worry about that?
No, never worry about giving us too little work. That's
Oh,
what I meant to say.
okay, got
That's
it.
what I meant to say.
Okay.
We're good.
We're always ready for too much work.
No. Sorry, everyone.
That was almost bad.
That was almost very
That was
bad.
almost really bad.
You didn't like my interpretation,
Yeah,
okay?
I
So
forgot
glad to
I
clarify
never
that.
signed my speech.
All right. So no questions? We're good?
That was very, very assuring.
You wanna say
Yeah.
that with confidence?
Maybe?
I mean, I could probably just ask it after class.
Yeah, we can talk after class.
Yeah.
All right, let's talk about continuity. And I want to introduce a special version. Did I spell it right? I sure did.
I think so.
Yeah, it seems like, right?
I'll buy that.
I think we know what that word is, no matter how it's spelled. I want to introduce this function that we're used to. Remember that the arg, the lowercase a arg of z is the angle made between the ray joining z to the origin and the positive real axis. So this is the arg of z can be that theta, and that theta is not unique. Right? We've talked about that many times. We've used that in all sorts of ways, that I can just add 2 pi k to that, where k is an integer. And so the arg function actually spits out infinitely many things. It spits out a set of things. So arg z, this is equal to a set of equivalent angles. That's not a function. Functions only spit out one thing. So this is like a multifunction of like a pretty high order. It's got infinitely many outputs. So let me write that here. Infinitely many outputs. Not a function, which needs only one output. So not a function, because the definition of a function is it maps an input to precisely one output. This is not a function. The minute I send one thing to 2 different things, that's not a function. It's not illegitimate, it's just not what we say functionhood is. So we're going to take this argument and create a special version of it. So we're going to define the capital arg of z. This is the principal. I gotta get which principal. Not the one who's your pal, right? The like main. The principal argument of z. And this is going to get us a function. Now we'll have a function. This, let me just look at my definition here. Basically is going to be an angle between, let's see, what do we do here? So I think, sorry, I'm just checking my notes to make sure that I'm getting this right. Yeah, the principal arg, if we're up here, it returns a positive theta, and if we need to come down here, then it's a negative theta. So from negative, positive, and it, sorry, I'm saying this really shittily. So let me just say it a little better than this. The principal argument is outputs a value. What is wrong? I'm speaking today between minus pi and pi. So that every z has a unique, well, Yeah, every z has precisely one argument associated with it. And we'll just pick, if it's down here, we'll pick the negative radian measure. If it's up here, we'll pick the positive radian measure. And like where this equal goes doesn't matter a whole lot. It kind of, I've seen it depend on different books. I think we'll put it up here on this thing. If you wanted a god-awful definition of this, and I know you do,
Of course.
why would you not? So if I've got z equals x plus iy, I can literally explicitly write this out with a, like I said, a god-awful, multi-piece function, piecewise. So when x is greater than 0, y is real. Y is always going to be real, so I'll stop being pedantic with that. So if we're over here, we're just going to return the arctangent of the angle. And that'll get you up to pi over 2 and negative pi over 2. And then we're going to do arctan of y over x plus pi if x is negative and y is non-negative. So this is the second quadrant. We're going to find the arctan of this and then just add pi to it. And then if we have we will spit arctan of y over x minus pi if we're in the third quadrant. We will, and here's a couple just like straight up and down cases, because you can't take the arctan of a 90-degree angle of pi over 2. So we just spit out pi over 2 if that should be the measurement. So in other words, if x is 0 and y is greater than 0. If you're on the positive imaginary axis, and we'll spit out minus pi over 2 if we're on the negative imaginary axis. And it is undefined if x and y are both 0, because there's no angle, and that makes sense. If you ever, like, I can't imagine us ever needing this formula. Like, we're not going to use it. Like, if you're writing a computer program, I could see that being useful, writing some code that you needed to produce the arg, but every programming language probably has a module that just does this anyway for you. I'm sure Python has a complex numbers package that we could easily just load in and do stuff with. So I just want that there because we're going to come back to it in a minute. It's an interesting function, but I want to just point out something to you. In the old arg, oh God, let's see if I can bring it up. Why didn't I do this earlier? Why didn't I do this? Oh, it's actually, okay, this might work. Things might work here. I want to show you a picture that'll be way more informative than my stuff. Who's the other user? Yeah, that's me.
Dr. T, is that the shirt that you wore to nonlinear dynamics and chaos?
It is. It's the logistic.
Did you wear it every day?
No.
That would be a mathematician thing to do, but
He did wash it between wears, I believe.
I did. No, it's just like it's a shirt I made. It's about the logistics bifurcation curve, and so it's like hidden math and like
So much
chaos and
math.
stuff.
Dang.
What?
Wish I could have done that.
I wish you could have too.
Never.
Man, I wish all of you'd freaking been there. We had like 3 people.
Hold it
Me,
next
Trinity,
semester and I'll be
Kayla.
there.
I can't, unfortunately.
No one can do anything next semester.
Nobody can do anything next semester.
Not that I'm.
Not that
I
you're.
can go to.
You can't go to modern geometry.
I've done it.
Fuck.
Yeah, I also can't take any math classes next semester.
You also had geometry.
No, but I'm not planning on taking that.
So you want to learn with the hyperbolic plane?
I'm done.
I just need numerics and then combinatorics, I think.
But you could come hang out with me and other math friends and do modern geometry.
It gets weird. You do all the
I
math
don't
around.
want to. I mean,
Oh, that doesn't look good.
almost.
What is it? Oh, is it like going to Windows 11? Like while we sit here? Okay. Oh, wow, that actually fucking works. So that's amazing. That is absolutely amazing. No, start with just let me go. Sure, I don't care. It's Regis' computer. Do whatever you want. There we go. So, oh, I hope I don't get in trouble with IT again.
Oh no.
Don't think the IT people do your class with you.
Alright, so I don't know if you've spent any time messing around with this beautiful site that I recommended. I still recommend it because there's so much fun in here, but let's go to what I want to show you today. Principal argument. Yeah, here we go. So there's some great visuals. So first off, there's the definition we just saw. And then here is, let's see. So hold on, there it is. Oh, there we go. Okay. So this is the argument function right here. So the vertical axis is just the angle that's coming out. And you've got this like infinite spiral. Now those things should actually be meshed. I'm not sure why they're not. Oh, I put it in spinning, that's pretty. So like, yeah, there's problems. Oh, I see what he's doing. He's actually showing the argument. So this is like principal argument that he's showing here. Notice how there's these jumps where if we were using instead the regular argument, just the pure argument, you would just keep, I'm gonna have to give those guys some money or something, I think he's asking for it. I'm feeling kind of guilty about it. But the regular argument, if you just keep spinning around the plane here, the angle keeps growing. So if you're moving clockwise, you just keep adding 2 pi, and you just see the angle increasing as you keep spinning. But with principal argument, let's look at the main branch. Principal argument looks like this. So notice that, here, let's see where we're at. So see there at the negative real axis, now we're looking straight down at it. Here's the positive real axis. That's where the value is 0. So you see 0 height there. And as you move clockwise, counterclockwise, your angle goes up to pi. So this is pi right here, the height. This is minus pi, the height. But look at that giant jump. So with the principal argument, as I come around this way, so I'm going pi over 2, 3 pi over 4, 5 pi over 6, I come up and I approach pi, and the minute I hit this axis, it jumps to minus pi. If I'm coming this way, I've got minus pi over 4, minus pi over 2, minus 3 pi over 4, minus 5 pi over 6, minus 11 pi over 12, and they keep getting closer to minus pi, and the minute I actually get there, oops, I jump. And now all of a sudden, it's positive pi. So look, I make a tiny move from here to here, and the value jumps like 6 points, 6 units, minus pi to pi. That looks broken. That's a discontinuity, which is what I'm really trying to point out here. That the pure version of this thing is continuous. If we look at that branch, which is a word we're going to use a lot in here, if I look at this main branch, the principal branch, it is broken. Cool. So now that I've been wanting to show you that picture since this class started. These computers have kept us apart. Now we're together. So let's talk about continuity so we can understand this a little more fully and talk about it, more intimately. We were talking a lot about intimacy in my Zen lab class right before our class, so I've got intimacy on the mind.
I'm a bit intimate with any of our students.
No, it's not that kind. It's not like pants off stuff. It's not bumping fuzzies, things like that. It's just
She was like in the middle of eating.
I'm so sorry. Should probably edit that video to avoid being in more trouble.
accountants here, none of us are gonna be mad at science, right?
No.
God, I hope no one was offended.
Yeah.
If you were, please,
Like, if you fail me.
please report me after class. I'll give you the form. They gave me a bunch of forms that you can report me with. They're like, here, you're gonna need these. Okay. No, it's just like being intimate with your life, right? Like appreciating, being vulnerable with what is, and being there in the moment, appreciating the sensation of this pen in my hand deeply.
Is this an RCC class?
It's RCC 200. It's I am going to teach a 400 version of it, but I couldn't do it next spring. I was supposed to, but
E1, you know which one?
it'll be meaning.
Damn.
It won't be next, it'll be spring of 25.
Yeah, I'll also be there.
Cool, well then take it.
I'm taking one now.
You can take another.
I would be
Going
going
after December, actually.
Oh,
Alright, the definition. Alright, continuity. So I've got this function f that runs from a subset of the complex plane and outputs complex numbers. That is the domain. That's all the values we've considered legit for this function. What's that?
Sorry, that's less than,
It's a subset.
a subset.
That is a subset sign, yes, sorry. And does that make sense, like, when I say that, or should I talk about what that means? Because not everybody's had, like, logic and proof.
I have lots of routine.
Yeah, so a subset, one set is a subset of the other. So first off, just think of sets as collections.
Yeah.
This says everything that's in this set is also in this set. So like the Venn diagram for this is I've got this bigger set, and A is inside of it.
I mean, in that case,
Say that again.
in that one we have, that one we written out there.
Yes.
It's the
Yes, so up there I'm saying that I've got G, which is just some part of the complex plane. Does that sound good? Cool, thanks for asking, I appreciate that. And that C is looking a little demented, so let me fix it back up. Okay, so, God, I hope, now I'm like, am I gonna get in trouble again? Oh, I don't want to,
No.
please, just come talk to me, don't report me. It's been enough this week. So suppose that Z is an accumulation point of G. No, sorry. So suppose G is a point in C. Z naught is a point in G. Sorry. Yeah. I had that written here, and then I was thinking, maybe it should be something else, but it should actually be this now. Or Z naught is an isolated point. Of G. So this is essentially saying the same thing, but I want to make sure that Z naught could be an isolated point. It could be just like, here's Z naught, here's G. It's all part of G, but it's kind of separated by itself. If the limit as Z goes to Z naught of f of Z equals f of Z naught, we say f is continuous at Z naught. That's the definition I'm going for here, continuity. Lots of ways, there's like it's not horrible, it's actually amazing and beautiful, but it won't go down as easily as this one. We've got like a delta epsilon version of this we could look at. It looks a lot like the limit definition, except you can actually get to the point. It's really just the limit definition, this thing, where Z can actually equal Z naught, and then the value of the limit is this point right here. So what I'm saying right now is this means three things. anytime you see a limit statement like this, three things are being implied. First off, one is that the limit exists. Because I couldn't write this equals something. So writing this something, that it equals some number, means the limit exists. Remember this one here? Let's just refresh our memory. We looked at that limit, and that limit could be anything. We could literally make that limit equal to anything by approaching 0 on the right path. Remember how we had it be 1 if we approach this way, and it was -1 if we approach straight up and down. So this thing here, we could get multiple values out depending on how we approached. So you want to have the same value no matter how you approach, because it's all about everything inside a disk. So we have to be able to approach in any crazy way and get the same number out to say this exists. So just saying that this is equal to something means that. Step 2 is writing f of z naught means that f is defined at z naught. Means f is defined at the point z naught. Your function needs to be defined at the point to even think about this concept. The function doesn't have to be defined at a point in limits in general, but for example, it's real simple. Let's say I had this function here. No, let me say this. So I've got this function here, so that's -1. This is just good old f of x, and this is x. Here the limit as x approaches 0 of f of x is what? -1, because the output is approaching -1 the closer we get to 0. So the closer the input gets to 0, the closer the output gets to -1. Doesn't matter how I approach, from the right or from the left, that's happening. But the function isn't defined there. I've got a big hole. There's no definition for the function. So limits can still exist without this happening. So what if I have the limit exists, the function is defined, and even more so, so look at this. Wait a minute. Ooh, now I made the function defined there, right? Limit exists, it's -1. Function is defined. Oh, it's equal to 1 at the point. So I have this, but that's not equal to f of 0. There's a big hole here, and that hole isn't filled. That's not continuous. What we want is the way this hole, this potential hole to be filled, is so that it syncs up with the limit. So that's the final part of this. Step 3 is that the limit equals the function value. That hole is filled in. And then, of course, we're in the complex plane, so, weirdness, craziness, just in general. Good. So let's get some nice examples so that we can feel safe and comfy with this. So many things are continuous. Lots of stuff is continuous. So first off, let's just do some examples and start off with a non-example and get that out of the way because you've already seen it. Arg z is not continuous on the complex plane because, so let's think about this. This is the principal arc. Let's take the point -1. Let's say z naught equals -1. And let's call this path 1, and let's call this path 2. As I approach -1 from the top, so in other words, the limit on path 1, as I'm just like implying here that path 1 approaches z naught. This is pretty abused notation. But the limit on path, how about we say that? On path P1 of arg z is what?
Pi.
Pi, beautiful. But the limit on half T2, which also goes to -1 of arc Z is, you wanna help me out with that one too, Lou?
Negative pi.
Thank you so much. It's negative pi. So I'm approaching the two different ways of getting two different answers. That's not what we want. In fact, the limit doesn't even exist there. That's part of the break of continuity. That coming in one way gets you here, coming in the other way, you're down here like, discrepancy. So we fail this. We're failing this aspect of continuity right off the bat. But what is continuous? So let's put that up here. Lots and lots of things, like I was saying, so any power of Z. So what is continuous? So all polynomials in Z. Does that make sense when I say that? Can you like picture what a polynomial is, or should I write that out? This is powers of Z, positive powers of Z. So integral powers of Z. That's the key thing here. Z to the fifth minus 2Z plus 5, something like that. Anything you put here as a polynomial that is continuous on all of C. When we have a function that is continuous on all of C, we have a special name for that. It's a whole class of functions, i.e. Polynomials are entire. So entire just means continuous on C. Wait, no, take that back. Not yet. Sorry, I'm jumping ahead. That's differentiability. That didn't sound right when I was saying it. Take that out. Sorry. Oh no! Right? So can you put differentiable functions that are differentiable on C are called entire? Does that help? I don't know. I'm just trying to help out here with your aesthetics.
Damn it.
Damn it! I know. I'm sorry. Sydney. And then many other things that I'm a little afraid to get into right now, but I will write them because they're kind of weird too. E to the Z. Now this is going to be a little weird. We'll get into this. We're going to spend a while just talking about functions. Let's see what other examples that I have down here. Oh, so here's a better one. Rational functions on their natural domain. What do I mean by this sentence? Can somebody help us out here? What's a rational function? Fractions, yes. Good. The lady knows how to do school. Fractions of what?
Functions?
Fractions of functions, that's even better. What kind of functions? Yes. Who said that? Was that you, Sydney?
Yeah.
Yeah, that's cool. I couldn't even tell. You were saying it so slowly.
I was
You were
hesitant.
almost not moving. So rational functions are just functions that look like this. It's a polynomial on top and a polynomial on the bottom. So each of these are polys. What does it mean to say their natural domain? What would be the domain of this function? Where would it be defined? Where would it not be defined is the better way to answer that. Yeah, and 0 where? So I love that's you're right. 0. Like if I put in 0 for Z,
No, when that's equal to 0.
yeah, when the denominator is equal to 0, right? We don't want that. So the natural domain is everywhere Q of Z is not equal to 0. So you just take out a few points in the plane and then it's good. It's continuous everywhere else. Here's one, kind of a nice one. Number 4, a nice simple one. F of z is z conjugate. Let's just think about why that might be continuous. So if this is my input, and I might want to use multi-hues here. I think I will hue this thing. So if this is z, now continuity means intuitively that if I change the input just a little, the output also changes just a little. There's no big jumps. Like with the principal arc, when we moved across pi, there was a huge jump in the values. So think about moving this to just z plus a little delta z. And then think about how conjugates work. Z conjugate, I'll do it in blue, z conjugate's just right here. And when I add a little, when I move this, its conjugate just moves a little bit here. So here is z plus delta z conjugate. Little move here produces a little move here, and there's no weird big jumps possible. So like just, I put that in here just because it's a really easy to see continuity. Small change in input results in small change in output, always, guaranteed. Okay, here's another function. Let's take a look at this one. I'm going to strongly recommend reading through the differentiability section in our book, or at least starting on that by Wednesday. Differentiability is like the deepest thing we'll have done, absolutely. Either that or go to the complex analysis online book and play with the differentiability section. That's also fun, lots of beautiful, fun apps to play with, right? We hopefully love that kind of stuff, or we are doing terrible things to our lives by being here if we don't love this. So what about this one? So f of z, I guess this is example 5. F of z is z squared if z is not equal to 0, and it's equal to 1 if z does equal 0. So do you think that's continuous? And if not, why? Where would be the problem with that, if anything? 0, yeah. Yeah, right? Because what is this? So let's look at this. The limit as z goes to 0 of this f of z, what is that limit? Remember, limits aren't about being at the point, they're being near the point. So as the input gets closer and closer to 0, which one of these two definitions will I use? If z is not 0, but it's tiny. Which of these two, do I go here or here? First one, right? Because this only kicks in when z is actually literally 0. If z equals 1 over a Google plus I over a Google, I'm still going to put it in the top. So it's a really tiny thing. What is this limit? What do you think this is? What does the output do as the input shrinks to 0? Gets smaller, right? So it actually goes to 0 too. The output shrinks to 0 as I approach 0. And you don't even look at this if you're thinking about approaching 0 as a limit. This is not about what happens at the point. And this is a strong example of that. However, f of 0 is 1. And it blows the definition because we have the limit as z goes to 0 of f of z is not equal to f of 0. The limit at the point is not equal to the value at the point, and that's not continuous. So this is not continuous at z equals 0, but it is continuous every other place in the whole plane. And I can't sketch that thing out because, again, 2 dimensions of input, 2 dimensions of output, that's a 4D beast. But we can kind of get a feeling for it. Let's intro to differentiability. We're not, I just want you to be vaguely familiar with these concepts. In real analysis, when you take that in the spring, if you haven't taken it, or if you have taken it, that's when you deal with this stuff. That's when you get into the definitions of epsilon and deltas. Complex analysis, for some reason, we don't do that. We actually have fun.
So, what happens when you raise a number to an imaginary number?
That's a good question. So we will get into that, but we already saw one example of that. Let me just kind of, remember this one?
Yes.
Let me refresh your memory, because I love doing this every time I do it. So what is the polar form of I?
E, so the I,
Pi over 2.
I will do.
Yeah, straight up, right? Straight up. And then what do I do with exponents when I have powers of a power?
You multiply them to get e to the negative power.
Yeah, so I get a real number. Not always, but in this one particular example. So we can do this, but before we do it, Noah, we actually have to talk about the natural log of a complex number, and that's like a whole day. We'll get there. Is that kind of like, yeah?
Yeah.
Yeah, we need this, because what we're gonna do, if I have like z to the w, what I'm gonna do is turn this into, let's see, how does this work? My brain is spacing right now. We'll get there. But we need this. This is absolutely essential. Because we turn everything back into statements of E. Oh, here's what it is. Okay, so Z is just E to the natural log of Z. These two undo each other.
Yeah.
So when I have Z to the W, that's E to the log Z to the W, and then that's E W times log of Z. And so once I understand how to do E to the Z, I can do all other powers and natural. Guys, cool, other questions or clarifications? Like, I just want to introduce differentiability, just a tiny bit. Because it's actually, let's just talk about differentiability in the real numbers, and then when we come in on Wednesday, we can talk about it in the complex plane. So let's recall, as a command. I command thee, recall. And you may or may not, that's okay. Every time you recall these things or see them again, they just get stronger. So, never hurts to go back to this stuff. We say that, so first off, let's just suppose I have a real valued function. And let's not worry about its domain. It just takes reals in and spits reals out. These are the things you've been spending your whole life on, except for this semester in this class. So you're well acquainted with these. We say f is differentiable at x naught if what? Yeah, recall.
It's probably continuous.
Definitely differentiability implies continuity, absolutely.
Gotta be able to look at it.
Yeah, it's pretty nice.
Proper term for a group of women?
Huh?
A gaggle.
A gaggle of women. It sounds cooler to you. It makes my heart a little bit happier than saying group.
Sydney always uses the weirdest words that I have to look up online before replying to your text.
I do not.
What do you have to like search up her words? What's this?
Whatever.
Anyways, differentiable.
By this point, Lavina speaks fluent Sydney.
I think we've all gained some competency in understanding Sydney's.
Sydney. I like that. I like that.
I like it too. If what?
So was the continuous part that he said not right?
Well, that it doesn't get us to the definition of. If we know it's differentiable, it will definitely be continuous. Continuity isn't enough for differentiability.
Limit exists.
It has to be a function.
So what, yeah, it has to be a function, yeah.
The limit exists.
Limit exists, it's gotta be defined at the point.
The limit is f of x naught plus, as a goes to 0, the limit of x naught plus a
Oh yeah,
minus the
that thing.
f of x,
Oh.
you get that whole mass. You
Okay.
know what I'm talking about.
I do know what you're talking about, that's what makes my heart sing, to hear you regale us with.
Anytime.
Thank you, yes. We'll go caroling
We
this
could-
season with the tales of differentiability. I'd rather hear this carol
And
than
hot
most
chocolate.
others. And what?
And hot chocolate.
And hot chocolate.
Beautiful. I'll be there.
Does this look familiar? Usually
Yeah,
you
it
see H here, but Noah's understands the definition, so he's just picking his own variables, so that's awesome. There. And let's talk about what that means. Let's think of the picture. So, it means that if I'm at x naught, and this is f of x, that if I move over a little, and here I'm assuming that h is positive, but if I drew it to the left, h would be negative, and we have to allow for h to be positive and negative approaching 0, because that's what this limit means. Remember, left side and right side have to be the same and exist. So here I'm just looking at the right side. And then that. So this right here is f of x naught plus h. This right here is f of x naught. We have this little picture. And really all we have here is the slope, right? This distance here is h. So we have the change in rise over the change in run. We have the slope of that, what's called a secant line. Yeah, does that sound okay, Sydney?
Yeah.
I know what means in Sydney.
Really?
Okay.
Let's pause, give you
Yes,
just
yeah,
a
it
second.
does, yeah, absolutely. Is this sounding familiar? Yeah, good. Okay, cool. So, as these 2 points coalesce, in other words, as h goes to 0, those 2 points coalesce, and if we think about this line extending in both directions, as those 2 points come together and become 1, we get the tangent point. So at the limit, after h actually approaches 0, we've got the tangent line slope. So once we get there, that's what we get. And so you use that in Calc 1, you're like, what's the slope of the tangent at this point? You take the derivative, and you do other stuff with it. So here's a different way to think about that I want to introduce that'll help us to think about what it means to be differentiable in complex number. Actually, first off, let's look at a non-example. So let's look at the classic, if I have f of x equals the absolute value of x. So that's this V shape. Does that sound right?
Yeah.
Yeah. This function is not differentiable at 0. Why is that? So this thing is not differentiable at x naught equals 0. Because if I'm doing this game that I was doing over there, so let's anchor that point there. Let's move over h units and go to that point. Then find the tangent line. Well, the tangent line has slope what? Or not, excuse me, what is the slope of the line between these 2 points? 1, right? Because this is just slope 1. And as h gets 0, does that change? As h gets closer to 0? No, so it's sloping all the way. So the limit as h approaches 0 from the right side, put a 0 plus, of f of x plus h minus f of, actually, let's put x naught, I guess. So here I'm saying x naught is 0 already. Over h is 1. Because that tangent slope is always 1 coming in from the right, whereas, so I'll put a but, limit as h approaches 0 from the left. What is this limit going to be from the left? What is the slope as if h was over here? H was a negative number. What is the slope between that point and 0?
Gina.
What are you saying?
Say it with your chest. She's been whispering the answer.
Yes.
Negative what?
-1. You heard it on the wind, now you hear it in life. There we go. So limit from two different sides gives us different values. So the limit, so this limit here does not exist. So the function is not differentiable at 0. It's differentiable everywhere else. Is this story, you've seen this story before? Yeah, cool. Always good to see this story again. So let me give you a slightly different interpretation and then we'll call it. And this is a cool way to think about it that you might have never seen before. So here I've got my input space, input, and then down here I've got output. And between those two I have a function, and this is real, so this isn't the real functions. Back to Calc 1. So let's say I've got this point x0 here, and I increment that by dx. So I just move over, let's say actually pretend it's almost like a vector of length dx. Let's just make that x. Sorry, sorry, Sydney. I'm sorry. So we take this point and we imagine a little bit of a perturbation away from it, dx. And then we pass that all through this function. So first off, when you pass x through, you're going to get f of x right here. And depending on what f is doing as a transformation, how it's stretching things, it's going to contract this or shrink or grow this. But down here, the amount that this infinitesimal change,
I like that one.
isn't that great? Infinitesimal. If you need help reading that spelling, I'm happy to oblige, because that looks pretty bad. This infinitesimal change here results in an infinitesimal change in the output, which we call df. And if I'm differentiable, small change here results in small change here. Whereas over there, you could think the change was like positive one way, but then all of a sudden it flipped to negative as I moved to the other side of 0. The key word is smooth. In the reals, differentiability is smooth. Small change in input results in small change in output predictably. Okay, that's it for today.
Beautiful.
Thanks. Indeed. Let's see if Lou, you saved us. You did it. Oh my God.